like to thank Professor Kwok, Professor Han for the invitation. And I do not know your background, so I will try to go slowly. If I need to go slower, please tell me. If you would like me to go faster, you can also tell me, but your colleagues may not be happy. So this will be a general lecture series about tensors and algebraic geometry with a focus on a particular problem that I will explain to you in a moment. So the story begins in 1969 when Strassen set out to prove something what he thought at the time, and everybody else thought at the time was obvious. That is, the way you multiply n by n matrices, you do kind of row column operations, then you do on the order of n cubed multiplications and about the same number of additions. And this standard algorithm for matrix multiplication has been around for a very long time. And Strassen set out to prove that it was the best possible algorithm. So the way you learn to multiply matrices in high school or junior high school, or maybe elementary school in Korea, because you're tough, is the best possible way to multiply matrices. And of course, that's a very difficult task to do. So he tried to prove a much more modest goal. He tried to prove that at least the algorithm for 2 by 2 matrices was the best possible. And in fact, he tried to prove the algorithm for 2 by 2 matrices just over a field with 2 elements is the best possible, because there were essentially a finite number of algorithms, and he could just go through the list of every possible algorithm. And much to his surprise, he found the following, which I've written small so you cannot see it deliberately, because you should not look at it very much. You should only look that there's these 7 pink multiplication symbols. And if you do this, take these additions and then multiply, these 7 multiplications, and then recombine, you get the product of this matrix and this matrix. You have calculated it by only using 7 multiplications instead of the usual 8. So this surprised him. Now, if we look at this algorithm, so the spectacular failure was can multiply two by 2 matrices using 7, which is less than 8 multiplications. But if you look at this formula, this x11, it need not be a number. It could be an element of an algebra. We could multiply matrices whose elements themselves were matrices. For example, this x11 could itself be a 2 by 2 matrix. All these entries could be 2 by 2 matrices. And so we could multiply 4 by 4 matrices using 7 squared, which is a lot less than 64. And in general, say 2 to the k by 2 to the k using 7 to the k, which is a lot less than 2 to the k cubed. And if what we get is approximately can multiply n by n matrices using on the order of n to the 2.81, Well, multiplications, but in fact, you could do even better with arithmetic operations. Because although the number of additions here is larger than the normal algorithm, when you do this trick of making your entries of your matrices smaller matrices, the number of additions grows more slowly. And really this multiplication captures the growth of complexity. So this was Strassen's spectacular failure. And then, of course, once someone has the idea that it's possible to do better, it brings about the question, how much better can one do? So let's make a measurement. Let's define omega to be the inf of all tau such that, well, let me say, let me give a name. So let's write Mn is the thing that eats an n by n matrix, eats a second n by n matrix, and I multiply it. This is the matrix multiplication operator. And we'll say that let omega be the inf over tau such that Mn can be computed with order of n to the tau arithmetic operations. So classical is that omega is less than or equal to 3. Strassen is that omega is less than or equal to 2.81 in this language. Now, what is absolutely amazing is there's been much research has led to the fact that omega is less than or equal to 2.38. So that asymptotically, it's much easier to multiply matrices than we might have thought. And this has led to a rather astounding, maybe even shocking conjecture that asymptotically it is nearly as easy to multiply matrices as it is to add them. I.e., more precisely, that this so-called exponent of matrix multiplication is equal to 2. that asymptotically you can almost multiply two n by n matrices using on the order of n squared arithmetic operations. Questions? Question?
I don't feel why it is so astounding.
So you think this is possible?
It's very big improvement.
I agree. This was in 1969, and there was steady progress, which I'll discuss. And this was in 1990. And many people since 1990 have worked very, very hard to lower this number. 2 years ago, there was some success that this fourth digit was changed. So essentially, since in 25 years, there has been no improvement, despite many people and many smart people working very hard. Of course, this means nothing. But actually, my intuition is when I first saw this conjecture, I thought this was a ridiculous conjecture. Now I only call it astounding.
Each group has been working hard.
It's a long list, and I do not have time. I did not prepare the long list. But we'll see some of the history in this lecture series. This lecture series will be about geometry. So there's a problem. Oh, yes?
I'd expect it to be 2.
Why do I expect it, or why do computer scientists expect it? I have no belief that this conjecture is correct. It may be correct, but I do not see any reason for it to be true or false. I will explain some geometric arguments that may lead you to think it's false, but those same arguments may lead you to think it is true. But I will talk about geometry in this lecture series. So what I'm going to do now is to slowly adapt more geometric language. Eventually, I'll be using the language of algebraic geometry. I don't know, how many people here have had at least one semester of algebraic geometry? Raise your hand. At least one semester. So not everyone, but most people. Okay. So, but today I will not introduce too much algebraic geometry, but I will at least need to discuss linear algebra to discuss these questions, because I come from a background of geometry, and in geometry we don't like formulas so much as invariant descriptions of geometric objects. So by the end of today's lecture, or at least by the end of this afternoon's lecture, we will be in the realm of geometry. So we'll start making that transition now. Yeah, I forgot this, yeah. So transition linear algebra, or multilinear algebra. Detour, although it's not a detour, so this is 2, this is 3, this is 4, 5, 6. Sorry. So I will work over the complex numbers in this lecture series, and I'll deal with complex vector spaces like CA, which is a dimensional vector space, but instead I'll just use the letter A, and similarly for CB I'll use the letter B, etc. Because the geometric things I want to talk about are independent of choices of coordinates. And when I write this, I mean we have literally column vectors and we've chosen bases. Here I just mean vector space. Now, given a complex vector space, we can look at the linear maps from our complex vector space to our ground field. And this space is also a vector space called the dual space. So this is F. So the set of such linear maps forms a vector space. It's of the same dimension. If we think of A as column vectors, and then A dual, we can think of as row vectors. So if we have A in, well, let's say X in A and alpha in A dual, if I write X is some X1 up to XA, alpha is some alpha 1 up to alpha A, then alpha of X is just this product. Row column, and it is indeed a number. Now, this matrix multiplication is not just a linear map, but it is a bilinear map. Well, first I need to do is say a little more. So let's let A star tensor B be the set of linear maps from A to B. So this is also isomorphic to A star tensor C, if you like. And this is a vector space. If I have bases, this is the set of A by B matrices. And I assume you've seen these things before. I'm just trying to fix notation. Now, this matrix multiplication here, if I call this A, I call this B, I call this capital C, this matrix multiplication is a bilinear map. So that is, if I fix an element here, the map from B to C is a linear map. And if I fix an element here, the map from A to C is a linear map. It is linear in each factor. And I'll let, so I will write Mn. If I write it this way, it will be an element of A star tensor B star tensor C, where A, B, and C are just the space of n by n matrices, which is just a vector space of dimension n squared. Now, I introduced this notation because this is too vague. And I would like a precise measure of complexity. So for linear maps, for a long, is it okay if I continue to use this board? The measure of a complexity of a linear map will say a linear map, F, has rank 1 if there exists alpha in A, B in B, and F is equal to alpha tensor B is a linear map. So this is a linear map from A to B. A goes to alpha of A times B. So this is the definition of a rank 1 linear map. and we say F has rank at most R if F is equal to some T1 plus plus TR, each Tj of rank 1. And in terms of matrices, this would correspond to the matrix representing this linear map having rank at most R. This definition generalizes very nicely to bilinear maps. We'll say F or T from A cross P to C, i.e. T in A star, tensor B star, tensor C, has tensor rank 1 if there exists alpha in A star, beta in B star, C in C, such that T is equal to alpha tensor beta tensor C is the bilinear map A cross B to C, where little a comma little b gets mapped to alpha evaluates on little a, beta evaluates on little b, and this gets multiplied by the vector C. In particular, its image is one-dimensional. And similarly, we'll say it has rank at most R. If it's the sum of at most R rank 1 linear maps. So we can rephrase omega. I will not prove this. This is a proposition due to Strassen that omega is equal to the inf over tau such that the rank of mn is less than or equal to n to the tau. So the proof of this proposition involves some technicalities from computer science, but it also involves something I said earlier that's very important. Namely, here we're dealing with arithmetic operations. This tensor rank, if you look, let me draw this pink dot. If C is a fixed vector, this computation involves essentially one multiplication. And here, to compute this tensor, I would have to do R multiplications at most. So what is implicit here is that this tensor rank is essentially capturing the number of multiplications one needs to do to perform the bilinear map T. And so there's kind of two parts to this proposition. One is that already over here I could have replaced this by multiplications. And then the second part is that this tensor rank captures the number of multiplications needed. But I will not prove these things. Yes?
You need to enlarge.
Hmm?
You need n large.
Yes. Oh, sorry. Thank you. Thank you. Okay. So failure can be very beautiful. So if I wanted to write this as a tensor, and if I write M, L, M, N, this will be the map from matrices L by M to the matrices M by N to the matrices L by N. As a tensor, or in this tensor notation, M, L, M, N, I could write as a summation. Let's say, let's write it as 3 summations. I equals 1 to M, X, I, tensor Y, I, J, say S equals 1 to N of Y, I, S, tensor Z, S, and say U equals 1 to L. So here's exercise. But maybe for this exercise, I should have made one remark, that this bilinear map I could also view, well, first of all, if I have T in A star tensor B, can also view as a map from A cross B star to our ground field, complex numbers, and similarly, T inside A star tensor B star tensor C, I could view this A cross B cross C star to our ground field. Namely, here I would have A and beta maps to beta of T of A, and here similarly A and B and gamma would map to gamma of T of AB. And it might be more convenient to think of it this way. So this is exercise 1. Exercise 2, if I view M, L, M, L, M, N as a map from matrices L cross M cross M, M cross N cross M, N cross L to C, this is matrices X, Y, and Z will map to the trace of X times Y times Z. So we have these different perspectives that we can use. Questions? So now we have a valid complexity measure. It's defined free of coordinates. There's no coordinates in this definition. So this is starting to look like geometry. Now, the next chapter in this story is 10 years later. And what's remarkable is it's also a story about a failure. So shortly after Strassen found his algorithm for 2x2 matrices, Vinograd proved that the rank of this matrix multiplication operator, so Vinograd So 1969, Strassen is that R of M2 is less than or equal to 7, and 1970s Winograd changed this to equals, that you cannot do better than Strassen's algorithm. So then Bini, Capovani, Lotti, and Romani said, well, maybe what if we do matrix multiplication where I set one entry equal to 0? So here, naive is, let's call this TBCRL, which is just matrix multiplication, except we set one entry equal to 0. Naive is that the rank of TBCRL for Bini, Capovani, LR, Lotti, Romani is at most 6, the standard algorithm. And they said, well, since we can't do better for this, maybe we can do better here. Now, even back in 1979, there were computers, and Bini was an expert in numerical methods. And he was trying to start out with a random algorithm and have it converge to this tensor by a sequence of iterated numerical approximation, something like Newton's method. The method he used is called alternating least squares. And it was very strange. His computer kept on getting very close to what he wanted. But every time he came very close to getting an algorithm, an expression, so he would get tensors that would get very close to this one. But as they got closer, something very curious happened. The coefficients would get very, very large or very, very small. And there was some strange thing going on that he did not understand. And I actually I've never met Strassen, but I met Bini. He's a wonderful person. And he was telling me this really caused him difficulty. He was unable to sleep at night. And then one night, somehow at 3 in the morning, he was trying to figure out what was the mistake in his computer code. And then all of a sudden, he realized that there was nothing wrong with his computer code. And he wrote the following thing down. For any epsilon greater than 0, this is clearly an expression of rank 5. There are 5. These tensors here are the 5 multiplications. And as epsilon goes to 0, this gets closer and closer to the tensor. So this, oh, I went out of order what I planned to say. That's okay. So this led, to the notion of border rank. So T has border rank at most R if T is equal to the limit of epsilon goes to 0 of some T epsilon with the rank of T epsilon equal to R, and then we write the border rank of T with the underline less than or equal to R. And then there's a theorem is that this is also a valid complexity measure. So that R of T is general less than or equal to R of T for any tensor, but despite that, Bini proved that this is also a valid complexity measure. So now we're dealing with the world of limits. What I would like to get to by the end of this lecture is the world of algebraic geometry. So let's start doing that now. Questions before I go on?
So in border rank case, the Bini's 5 is the optimal.
Yes, but that was only proved much later. In 1985.
Can they be actually different numbers?
Yes, I will give you an example. And well, for this tensor, the numbers are different. The rank is 6 and the border rank is 5. But I will give you a much simpler example, maybe right now. And also, this simple example, so I'm happy if you ask questions, but it may change the order of the lecture, so the outline may not be correct anymore. But let's look at T equal to x1 tensor y1 tensor z2 plus x1 tensor y2 tensor z1 plus x2 tensor y1 tensor z1. Exercise R of T is equal to 3. You cannot improve this. But T is equal to the limit. Actually, maybe I'll use little t goes to 0 of 1 over T x1 tensor y1. Let's do it this way. x1 plus t x2 tensor y1 plus t y2 tensor z1 plus t z2 minus x1 tensor y1 tensor z1. And now let me give a very important picture. This is my favorite picture. So think of this curve as the set of rank 1 tensors. It's not really a curve. It really has higher dimension, but that's okay. And let's look at this, say, this point here. Let's say that this one happens to be x1 tensor y1 tensor z1. And then we add a little bit to it. Let's say that this one here is x1 plus t x2 tensor y1 plus t y2 tensor z1 plus t z2. And this point for any fixed t is some point on this line. Here's our point. Let's call this t sub t. This is my t sub t, is some point on this line. I'm adding them together. Now what happens when t gets close to 0? This other point is moving closer and closer to my initial point. And my final point, t, is sitting somewhere here. So if we visualize this as a curve in 3 space, the points that have tensor rank 2 lie on a proper secant line to the curve. The points that have border rank 2, did I use that term? Border rank, yes. The points that have border rank 2 are those that lie on a limit of secant lines. And as we learn in calculus, or maybe even before, the limit of secant lines is a tangent line. So there is a very good geometric reason for this difference. Other questions? Good question. Now, we've already seen that differential geometry of secant and tangent lines, is going to play a role in our story. Now I would like to show you how algebraic geometry is going to play a role in our story. So, we have this astounding conjecture that omega equals 2. So let's say you're like me and you're skeptical how to disprove the astounding conjecture. Well, I want to show that the rank of this matrix multiplication operator is greater than some R0, where for each R, this will depend on n. And where this function R0 of n grows faster than n squared. Right? And let me just, in case you're an optimist like Professor Kwok, how to prove astounding conjecture. Want to show that R of Mn is, say, less than, well, let's use another letter, capital R0, some capital R0 of n, where this is faster than n squared. Well, faster than n squared. And this one is slower than n squared plus epsilon. Well, since I'm lecturing and not Professor Kwok, we'll start out pessimistically. So here's the idea. Well, we have our space, Cn squared tensor Cn squared tensor Cn squared, and we have our point in that space. And also inside this space, we have the set of T with rank of T less than or equal to R0. So here's our picture. We have the whole space. We have this set. And we have our point, Mn. And I want the picture to look like this. I want this point to not be inside this set, because I'm a pessimist. So, how to disprove? Here's the idea. And this is the first entrance of algebraic geometry. This is a vector space. What is it? It's Cn to the sixth, I guess. Right? It's just some very, very large vector space. And we could look for a polynomial P on this vector space such that P of T is equal to 0 for all T with rank of T less than or equal to R0, everything in here. So the 0 set of P may be larger than this, but we just want it to not vanish at R point. This is our idea. So algebraic geometry is about the study of polynomials, study of zero sets of polynomials. We want to find a polynomial whose zero set contains this, but does not contain this. That's our goal. So coming attractions, well, I will present some polynomial to you in the course of the week that gives that. Maybe not enough to disprove the conjecture, but it'll give you a lower bound on the complexity of this tensor, a lower bound on the rank of this tensor. Now let's say we want to prove the conjecture. Well, incorrect, but I'll present it. Idea is to find a collection of polynomials say P1 up to PQ, whose zero set is exactly this set, such that T, the rank of T is less than or equal to R0 if and only if P1 of T equals 0 up to Q of t equals 0. And then show that P1 of Mn equals 0 up to PQ of Mn equals 0. This is the idea. Why is this idea incorrect? What's wrong with it?
You have to show that the end when the tensor is inside the interior of the variety.
Exactly. Let me give a simple example. Let's consider the set S contained in complex 2 space. And S will be the line, say if this is Z and this is W, this is the set Z comma W such that W equals 0 union minus the origin. So this pink set S. Now, what are the polynomials vanishing on S? Well, it's easy. Any polynomial, let's restrict to homogeneous to make our lives simpler. These are the polynomials that, that are divisible by W, right? So the zero set of these is not equal to S. The zero set is strictly larger than S. The zero set looks like this. It's the whole line. That is, polynomials are unable to see this point. So when we have a set, so now I have my vector space A, and I have some subset Z contained in A. We'll define the Zariski closure C bar to be the zero set of all, polynomials vanishing on Z. So the problem with this plan is what we will find is not the tensors of rank at most R by polynomials, but the polynomials can only detect the Zariski closure of the set of tensors of rank less than or equal to R, R0. That's the problem with this plan. So the plan with polynomials is fine without any modification for disproving the conjecture. But if you want to prove the conjecture, there's a subtlety. Now, at this point in our story, we've seen two subtleties. We've seen this issue about closure under limits, Euclidean closure, and we see this issue of closure under Zariski closure. And I've already told you that closure under limits actually does not cause a problem. Bini proved that if you take closure under limits, asymptotically, you get the same complexity measure. And now we have a different issue. What about taking Zariski closure? Do we get some different complexity measure? So the following theorem says no, that we're okay. And this theorem you can find in Mumford's book on complex projective varieties. Oh, let me introduce a little notation. So I really would prefer to work in projective space and with homogeneous polynomials. So if V is a vector space, I'll let PV be V take away the origin minus an equivalence relation where V is equivalent to W is the same as that V is some lambda W, lambda a non-zero complex number. And we have a map from V minus the origin down to PV pi. So if I have V in V, I'll let bracket V be pi of V. This is all notation. And if I have Z in PV, I'll let Z hat be pi inverse of Z union the origin, which is often called the cone over Z. And we can go between projective space and vector spaces. I want to go in projective space. A very good justification is the following theorem, which is false in affine space. Well, I'm not sure it's false enough. Let me erase that last sentence, please, for the tape. It's a different theorem I was thinking of as false. Then I have some subset. Then this is the easy part. Then the Euclidean closure i.e. closure under taking limits of Z is contained in the Zariski closure. And 2, if Z, so if U in PV, if U in PV is such that U bar equals U, we say U is Zariski closed. And PV take away a Zariski closed subset is Zariski open. And more generally, a Zariski, the complement of a Zariski closed set inside another set is a Zariski open subset of that other set. If Z is a Zariski open subset, of its closure, and Z bar is irreducible, I forgot to define that, but I will later, then the two agree. The Euclidean closure and the Zariski closure agrees. So one direction in this theorem is very easy. It's very easy to see that if a polynomial vanishes on all points on all secant lines, the polynomial must also vanish on points on tangent lines just by continuity of polynomials. The other direction requires a little bit of work. I think I will not even give the outline. Okay, maybe, so I was going to give an overview of the lecture series, but maybe we can do that this afternoon. And I can just give a few more definitions now. And then you'll have to come this afternoon because the overview is the most entertaining part. Whereas the definitions are boring, but now you're tired, and so there's no point having something interesting just before lunch when we're going to have an interesting lunch. So I'll have something interesting in the afternoon when we're tired. So, so if we have X zero set of a collection of homogeneous polynomials, means that really X hat is the zero set. And the point is if we use homogeneous polynomials, the zero set will indeed be a cone. So it makes sense. And we say X and call such an algebraic variety and we'll say X is irreducible if it's, or well, let's say X is reducible if X can be written as Y union Z, where Y and Z are algebraic varieties and non-trivial. And otherwise, X is irreducible, which is the word I used in the statement of this theorem. It cannot be written as the union of two sets, because otherwise it could be an open subset in Y, and you would just end up with the closure of Y under Euclidean closure. So that's definition. Time. Okay. So let me rephrase now what I was saying before. So thanks to this theorem plus Bini's theorem. So first of all, says that the set of T, set that the border rank of T is less than or equal to R0, is Zariski closed, and it's sufficient to carry out the program with this set. So we can find a collection, by definition, we can, or by this theorem, we can find a collection of polynomials whose zero set is exactly this set. If we find such a collection, then we can test it on matrix multiplication. The price we will pay is it may not be possible to write matrix multiplication directly as a sum of R0 rank 1 tensors, but for the purposes of complexity, asymptotically, this does not matter. Okay? So this afternoon, I will give you an overview of the lecture series. The first few days will be material that has been around for a little while. Most of it is available in my tensor book that's over there. And the rest is certainly available in this book on my webpage that I'm currently writing. Later in the week, I will be talking about more recent work so most of the work of algebraic geometry has been about trying to prove lower bounds on the complexity, just because it's easier to find one polynomial than a collection of set theoretic polynomials. And much of the early part of the week will be in that direction. Later in the week, there's some new ideas from geometry that may be useful for also proving upper bounds, not by this plan, which actually is a very difficult plan, it turns out. It's a correct plan, but it turns out to be difficult. But by other methods that will explore the geometry of algorithms. And for example, how could a geometer have found Strassen's algorithm? Or how could a geometer have found Bini's algorithm? I'll discuss this a little bit this afternoon and more extensively later in the week. Thank you for your attention.